All right, so we're doing linkages, and I'm just going to go through some problems. We'll have a little time either today or next class for you to work together in groups on one of these, try to solidify this stuff. But, all these problems are pretty much the same once you get used to it. So let's call this member 1 and this member 2 and joints A, B, and C. And the first step in any linkage problem is just do all the rigid body calculations, do the rigid body kinetics for each member. So I'll start with member 1. Does member 1 have a fixed point? And so that means that our about point is going to be A, that joint A. And now second, mass moment of inertia. When you have a fixed point, you most often have to use parallel axis theorem. So the moment of inertia about A is 1/12 times the mass. Wow, 100 kilograms. That thing is big. So 1/12 times the mass times, this is a slender rod, so times 2 squared. And then plus the parallel axis theorem part, which is the mass, times, someone give me the definition of that distance D.
The distance from the about 40 inches. Okay.
From the center of mass to the about point. And so in this case, from the center of mass to the pin. So if the whole thing is 2 meters long, that distance is 1. We square that. And so we have, let's see, so this is going to be 33.3 plus 100. I think that's 133.3 repeating. Yeah. And now I'll do the free body diagram. There is a weight force acting at the center of mass. That's 100 times 9.81, so 981 newtons. Over here, there is a reaction force with the wall. I'll call that RA. It's unknown, so it's a full force vector. And then over here, we have the force vector, since that's also a pin, the force on 1 by 2. Any questions about that? And then we'll go to the table. Our about point is the fixed point. So I'll start with RA. That force RA is at our about point, so the row vector is 0. What's the definition of the row vector?
The distance from
Not the distance. The
vector
vector, yeah.
from the about point to where the force is.
Right, exactly. The vector from the about point to where the force is applied. The force is RAX, RAY. Cross product is 0. Then the weight force, that row vector is, so from the about point to where that force is applied, so that is 1, 0. The force is 0, negative 981. Cross product is negative 981. And then last is the force F12. The row vector is 2, 0. The force is F12x, F12y. Cross product is 2F12y. Any questions about that? Do we need Newton's second law?
No, there's fixed.
Right, so we'll go straight to rotational Newton's second law. And so that says negative 981 plus 2F12y is equal to 133.3 repeating alpha 1. And I'll write this as our first equation from the big system we're going to get. And I'll rewrite this as 2F12y minus 133.3 repeating alpha 1 is equal to positive 981. Okay, how many variables do we have so far? Well, look at the equations, not the free body diagram. So right now we have one equation, only two variables because no F12x appears in our list of equations. That's still not enough equations to solve it. So in the end, we're going to just have this big system. And now we'll go to member 2. And that angle is 60 degrees. That member is 1 meter long, 50 kilograms. So step 1, does member 2 have a fixed point? Nope. So it can slide left or right at C, so that's not fixed. And as this pair of things moves around, B can move, so no fixed point. And so our about point is the center of mass of member 2. And the moment of inertia about the center of mass of 2 is 1/12. This is another slender rod, times the mass, times the length squared. And so that is 4.16 repeating kilogram meter squared. And then free body diagram. We have a weight force acting at the middle. So that's 50 times 9.81, 490.5. Up here, we have a pin joint. So we know that's an unknown force vector. That's the force on 2 by 1. But Newton's third law says that that is negative force on 1 by 2. Any questions about that? Okay, and then the last force comes from that pin and slot joint. And rollers and pin and slot joints both do the following thing. They don't apply any force along the slot because this thing is free to move that way. Okay, but it's not free to move perpendicular to the slot. So we know that that's a force perpendicular to the slot. Otherwise, it would jump up or sink down or whatever. Okay, so you can put that force in either direction that's perpendicular to that slot. There are always two vectors perpendicular to any line. I'm going to put it up, but you could put it down. It'd be fine. If your guess was wrong, you'd just get a negative and everything would, it would tell you the story anyways. Okay, so that slot is horizontal, which is nice. We don't have to mess with angles or anything. And so that force is just straight up or straight down. And I'll call this RC, but notice that that's a scalar because we already know the direction. We just have to know what to multiply by a unit vector in that direction to get the full vector. Any questions about that? And now we'll go to the table. Rho, force, moment. Okay, so this time, remember our about point is here. So I'll start with the weight force. The rho vector is 0 because that force is at the about point. The force is 0, negative 490.5. Cross product is 0. Then we have the force negative F12. So let's see. From the red dot to here, the whole thing has a length of 1 meter. So from the red dot to the end is a distance of 0.5. It's at an angle of 60 degrees counterclockwise from the horizontal. So this is 0.5 times cosine and sine of 60 degrees. So that is, so cosine and sine of 60 degrees gives you a unit vector that is 0.5, 0.866. And 0.5 times that is 0.25, 0.433. The force vector is negative F12x, negative F12y. Cross product is negative 0.5 F12y plus 0.433 F12x. Any questions about that? Yes.
Is it negative 0.5 F12y or is it negative 0.25?
0.25, thank you. Negative 0.25. Okay, and then the last one is RC. That rho vector is, well, one way you can think of it is it's the exact opposite rho vector of the one we just did, so you can just multiply by negative 1. It's the same vector, just in the exact opposite direction. Or you could think of it as 60 plus 180 gives you 240. So it's 0.5 times the cosine and sine of 240 degrees. That's straight up the way I have it drawn, so 0 RC. And so the cross product is negative 0.25 RC. Any questions about that? Do we need Newton's second law for this one?
It's not fixed.
Not fixed. So yes, we need it, exactly. So Newton's second law. We're going to take all of these forces and set them equal to mass times acceleration. So we have 0, negative 490.5. plus negative f12x negative f12y plus 0 RC is equal to the mass times the acceleration of the center of mass of body 2. I'm always just going to write that. The only time we have these acceleration variables is when we're calculating accelerations of the center of mass. So I'm going to write this as a2x, a2y. But remember that that's the acceleration of the center of mass of 2. Okay. I'll rearrange these. So we get an equation 2 star that says negative f12x minus 50 a2x is equal to 0. And equation 3 star says negative f12y plus rc minus 50 a2y is equal to 490.5. And then rotational Newton's second law. For this one, we're going to add up all of these moments and set it equal to I alpha for body 2. What point on body 2 are we calculating alpha for? So remember, for the acceleration, we're calculating the acceleration of the center of mass. What point on the body are we calculating the angular acceleration for? This is a trick question. It's all the same. A rigid body only has one angular acceleration, but every point has a different acceleration. Okay. Okay, so I'll rearrange these just to put them in X, Y order. So 0.433 F12X minus 0.25 RC. Nope. Minus 0.25 F12Y minus 0.25 RC is equal to the moment of inertia of this body, 4.16 repeating, times alpha 2. And this is our fourth equation. So I'll write this as 0.433 F12X minus 0.25 F12Y minus 0.25 RC minus 4.16 repeating alpha 2 is equal to 0. This is our equation 4 star. Okay, so we have 4 equations now. Let's see how many variables we have. So we have F12Y and alpha 1. Here we also get F12X. So we have, I'm going to just start writing them down. We have F12, X and Y. We have alpha 1. We have RC. And we have the acceleration of the center of mass of 2 X and Y components. So I'll write that as A2. So how many variables do we have? 2 here, 2 here, so 4, 5, 6. Uh,
Alpha to the map.
and alpha 2. Thank you. Yes, very good. So 7 variables. And I was careless and I missed that variable, but I would have noticed that I had missed it at the next step when I start thinking about how many constraints I'm going to have. Okay, so now let's start thinking about, so how many constraint equations do we need? Yep, exactly. We need 3 more equations without introducing any new variables in order to solve this. So 7 minus 4 equals 3 constraint equations. And where are they going to come from? So let's think now about what they will be. So first, we'll have an equation that says the point B on body 1 has to have the same acceleration as the point B on body 2. Okay, so I guess I'll write that as the acceleration of B according to body 1 has to be equal to the acceleration of B according to body 2. That's an x and a y component, so that's 2 equations. Okay. So now we need one more constraint equation. Let's think about where that'll come from. Well, this point C on body 2, it can accelerate left and right. So we have nothing to say about the horizontal acceleration, but it can't accelerate at all up and down. That slot won't let it. Are you with me on that? And so we are going to calculate the acceleration of C according to body 2, but then we're only going to set the y component equal to 0. So I'm going to say the acceleration of C according to body 2, y component, that's crazy notation, is equal to 0. And that's our one extra equation. And so if I had, not had someone catch me missing this alpha 2 variable, I would have come down here, thought about where my constraint equations are going to come from, and say like, that's not right. And then I would have gone back and found my problem, When you make as many dumb mistakes as I do, that's a very crucial step.
For every problem, there's a different constraint equation. Like we need to find it out, like, looking at the problem.
Well, yeah. So every pin joint connecting 2 bodies will have a constraint like this. Okay.
So they will always have the same acceleration.
Right. Yep. So all it's just saying is at that point, body 1 and body 2 can't fly apart. Okay. So that's why those accelerations, whatever they are, whatever this does, those 2 accelerations have to be the same. Okay. Yes.
We can only get those constraint equations from pin joints. Is that the only place we can?
Well, you can also get them at, so this second type could be a roller or a pin in a slot joint.
Oh.
And I think that's the only kind of things that we deal with. You also could have pin and slot joints connecting bodies. I don't think I give you any problems like that. But then the component of acceleration perpendicular to the slot has to be the same for the 2. But I don't think I give you that. You can, if you ever need that for a research project or whatever, you can look it up. Or, these are the more common ones. Oops. Okay, so let's start finding these constraint equations. So first I'm going to do the constraint at B. And that says that the members can't fly apart at B. So I'll start with member 1. So how are we going to calculate the acceleration of B according to member 1? Well, member 1 has a fixed joint, and so B is just in circular motion around that fixed point.
Watermelon equation.
Yeah, exactly. So all we need is the watermelon equation. We don't need any relative motion equations. So we'll go acceleration of B is equal to alpha cross R plus omega cross quantity omega cross R. Our alpha, we don't know what that is yet, but we do have an expression for it. This is 0, 0, alpha 1, because right now we're doing it according to member 1. Our omega vector, it's given in the problem that at this instant, we're looking at this thing at rest. So the angular velocity is 0. And then someone give me the definition of the R vector.
About point two.
From the center of the, yes, basically. From the center of the circular motion to the point of interest.
Yeah.
Yep. And so the center of the circular motion is A, the point of interest is B, the length is 2, so that's just going to be 2, 0, 0. Come on. Okay, so the acceleration of B is 0, 0, alpha 1 crossed with 2, 0, 0 plus this stuff, which goes away. And so we get 0. So minus alpha 1 times 2, but then y always has to be the difficult one, so it's plus 2 alpha 1, 0. And now we'll do the same thing for member 2. Okay, so this one has a fixed point. This one doesn't. So this one we're going to have to use relative motion. And that intermediate point that we're going to use for relative motion is the center of mass, because we already have an expression for the acceleration of the center of mass. So this, we're going to go acceleration of B relative to the ground is equal to the acceleration of B relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. This is our A2 variable, and this is the watermelon equation. Right? So the acceleration of B relative to the center of mass of 2 is equal to alpha cross R plus omega cross quantity omega cross r. And it just sort of pops into my head as I do this. Like, I'm writing down so many steps, but the more steps, like, you're not going to be racing against the clock when you're doing this stuff on tests or whatever. I'm going to always give you plenty of time. There's no reason to feel rushed. The more steps you write down, the more you can go back and find where things went wrong, you know? So I would say take your time. You know, it's good to save paper. It's good for the planet, but have some confidence in yourself that once you're a working engineer, you'll have more ability to save the planet than all the paper you wasted. Okay, so don't worry about writing stuff down. Okay, so alpha 2, well, I guess the way I wrote it is, our alpha vector is 0, 0, alpha 2. Our omega is 0. And our r vector, that is from the center of the circular motion to the point you care about. The center of our circular motion here is the center of mass of 2. And so this is going to be 0.5 times the cosine and sine of 60. So this is going to be 0.25, 0.4330. And so I have cosine and sine memorized for a lot of angles, and then so I can multiply very simple numbers times those. So the acceleration of B relative to the center of mass of 2 is equal to 0, 0, alpha 2 crossed with 0.25, 0.4330 plus this stuff that goes away. And so for an x value, we get negative 0.433 alpha 2. For the y value, we get positive 0.25 alpha 2. And for z, we get 0. And so the acceleration of B relative to the ground is equal to negative 0.433 alpha 2, positive 0.25 alpha 2, 0, plus the acceleration of the center of mass of 2 relative to the ground. That's a2x, a2y, 0. So I guess I'll write it one more time as negative 0.433 alpha 2 plus a2x and positive 0.25 alpha 2 plus a2y and then 0. And so our next two constraint equations are just setting this vector equal to this vector. So we have 0. So let me, finally we're at the constraint equation. So 0, 2 alpha 1, 0 is equal to negative 0.433 alpha 2 plus a2x, 0.25 alpha 2 plus a2y, 0. one of these equations says 0 equals 0. That's a good reminder if you forget what 0 is equal to, but it doesn't help solve any systems of equations. So, our equation, what are we on? Equation 5 star, finally, is 0 is equal to this. And I'll write that as negative 0.433 alpha 2 plus a2x is equal to 0. And our equation 6 star says, remember you have to get all the variables on one side, so I'll write that as 0.25 alpha 2 plus a2y minus 2 alpha 1 is equal to 0. Okay? We have one more constraint to go. So this is the constraint at C. And all we're doing here is saying that on body 2, that point C cannot have any upward or downward acceleration. So we're going to do that by calculating the acceleration of C using body 2. Body 1 doesn't touch C's, that's why we don't care about that. And then we'll just set the y component equal to 0. So we're looking at member 2. And we have that member 2, remember, doesn't have a fixed point. So we're going to use relative motion again. The acceleration of C relative to the ground is equal to the acceleration of C relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. And again, this is just our A2. And again, this is just the watermelon equation. So the acceleration of the point C relative to the center of mass of 2 is equal to alpha cross r plus omega cross quantity omega cross r. And our alpha, since we're looking at member 2, this is 0, 0, alpha 2. Our omega is 0. And our r, so r goes from the center of the circular motion to the point you care about. The center of our circular motion here is the center of mass of 2. The point we care about is C. So this would be, you could go 240 degrees, or you could go negative 120 degrees, or you could recognize that it happens to be the exact opposite r vector of that we used in the first constraint equation. But r is equal to negative 0.25, negative 0.433, 0. And so the acceleration of C relative to the center of mass of 2 is 0, 0, alpha 2 crossed with negative 0.25, negative 0.433, 0, plus this stuff that goes away. So you get positive 0.433 alpha 2, and negative 0.25 alpha 2, and 0. With me? Disagreements? Yeah.
When you're making that R vector, how do you know that the center of circular motion is at the center of mass of body two and not like the point B?
One way to do it is when you're using relative motion equations, when you're using the watermelon equation along with relative motion equations, this always tells you what the center of your circular motion is. So think the meaning of those relative motion equations is, or the meaning of A, acceleration of C relative to the center of mass of 2, is saying, imagine the center of mass of 2 is not accelerating, and calculate based on that what the acceleration of C is. Well, if we're assuming the center of mass of 2 is not accelerating, then that's the center of our circular motion. But yeah, the too long didn't read version is if you have it written out in relative motion, what you're doing at relative to is the center of your circular motion. Okay. So this is the acceleration of C relative to the center of mass of 2. Now we have to use the relative motion equation, add on A2. So the acceleration of C relative to the ground is 0.433 alpha 2, negative 0.25 alpha 2, plus A2x, A2y, 0. And now we want to set the y component equal to 0. And so our final equation, equation 7 star, says negative 0.25 alpha 2 plus A2y is equal to 0. Okay, and our variables, we have 7 equations. Hopefully we have 7 variables. And those are the variables that we have are, don't look at the free body diagrams, look at the equations. If you look at the free body diagrams, the first variable you think we have is R, RAX and RAY. But if you look through the equations, those never show up. So that's not part of our system, okay? If we wanted, we could calculate those later, but those aren't part of our system. So the variables we have are F1, 2, X and Y components. A2, X and Y components. So now we're at 4. Alpha 1, 5. Alpha 2, 6. And the known direction force, RC, 7. Okay, so 7, that's not too horrible. I mean, this process was long. It's not too horrible to solve this now. We'll use reduced row echelon form. So I need 7 rows and 8 columns. 1, 2, 3, 4, 5, 6, 7, 8. So that's good. And those correspond to my variables and my constants on the other side of the equation. So this is going to be, I'll do it, F12x, F12y, A2x, A2y, alpha 1, alpha 2, RC, and then these are the constants. Okay. And then I need 7 rows. And each one of those represents one equation. So I'll do this as equation 1, equation 2, 3, 4, 5, 6, 7. And now we just have to go back and find the coefficients of all these things for each equation. So for equation 1, actually, would you guys mind just reading me coefficients for these? So just tell me like F12Y 2, and I'll fill it out so I don't have to keep scrolling back and forth. So on equation 1, shout it out. Let's go around like a wave in a, no, let's not do that. Okay, so F12X, right, was 2. Is that what it said? That's the only one I paid attention to. What? Oh, Y. Sorry. Thank you. Got off to a bad start. Okay, so this is 2. Okay. Okay, negative 133.3 repeating. Okay. 981. Okay, equation 2. Negative 1. Okay. Negative, for A2x. Negative 50. Okay. Okay. Negative 50 here.
And then 1 for RC. And then the constant is 4.
Okay. Zero 0.433. Okay. 0.25. Okay. Yep.
And then RC is 0.25 negative.
Okay.
And then negative 4.16 repeating for alpha 2.
Oh, okay. On the same one still?
Yeah.
Negative, did you say?
Yeah.
Negative 0.41. Oh, got it. Negative 4.16 repeating. Okay. And that one doesn't have a constant? Oh, right, because it doesn't, because it's at the about point is the center of mass. And then equation 5.
That's 0, 0, 1, 0, 0, negative
0, 0, 1. And then, sorry, start there.
2 more zeros and negative 0.433 for alpha 2.
Okay.
No constants.
Okay.
And then row 6 is 3 zeros multiplied by 1, negative 2, and 25. No constants.
Okay, so after the 1, what happens?
Negative 2 and 0.25.
Okay.
That's it. And then 7th row is 3 zeros, 1, 0, and followed by negative 0.25.
And that's it? Okay. So why doesn't everybody punch this into your calculators and we'll all see what we get. And hopefully out of the 35 of us or whatever, two of us will get the same thing, and we're going to call that the answer. Thank you. Okay, what's the acceleration of the pin along that slot? Well, somebody give me the y component of the acceleration. 0, yeah. Yes.
I was going to say you can, if you find the acceleration of that point C, you could use the center mass of the entire system, right? And then use that force.
We have an easier way than that, actually, because so notice that we already have in our constraint, so our constraint at C, we already went through all this work to calculate the acceleration vector. So now we can just plug in the values. We know that the y component is 0 because that was part of the definition that gave us these answers. And so what about the x equation? So we have 0.433 alpha 2 plus a2x. So the acceleration of C relative to the ground is equal to, I already forgot it, 0.433. Okay, 0.433 times alpha 2 plus a2x. This one was negative 0.25 alpha 2 plus a2y. Now we can plug in our values. So we have 0.433 times negative 14.715 plus, I guess that's a minus, 6.37. And this one comes out to be 0. We already know that. And so this comes out to be negative 12.7400. If you look at this problem, what happens is as this thing collapses, that pin at C accelerates to the left, and the magnitude of that acceleration is 12.74 meters per second, like just over 1 g of acceleration. If you want to use that to open a walnut or something, whatever your application is for this machine or whatever, that information is useful for whatever you're trying to do, I don't know what acceleration a walnut shell needs to open, but what? Yeah, I don't know. What if we wanted to calculate the reaction force at A? Notice, that didn't come up in our equations. How would we do that? Perfect. Yep, exactly. So now we have all these values. We can set, well, first, I guess the first step is we have to calculate the acceleration of the center of mass of 1 based on the values we have. That's just a geometric thing using circular motion, the watermelon equation. Then once we have that, we can use Newton's second law and calculate RAX, RAY. Well, we have a few minutes. Why don't everybody take a few minutes and see if you can calculate that force vector RA.
Acceleration of B with respect to the ground? Particular motion?
No, you don't have to because we have the fixed point.
Oh, yes.
So the fixed point is just the center of your circle. So now calculate this force vector RA. Is alpha cross R plus omega cross quantity omega cross R. This is 0. Alpha is, so this is for body 1, so that is 0, 0, negative 3.68. And R goes from the pin joint to the center of mass, so that's 1, 0, 0. And so you get 0, positive 3.680. It should be negative. Yes, that does not make any sense. Whoops, and this is not alpha, this is the acceleration vector. Okay, who needs more time to plug this into Newton's laws? I'll give you a couple minutes to do that, and then I'll plug it in and we'll calculate that reaction force. So let me do Newton's second law. I'm just going up here. We already have these forces listed out. This one. So I'm just going to add these up and set it equal to the mass times the acceleration of the center of mass. We have F12x, F12y, plus RAX, RAY, plus 0, negative 981, is equal to 100 times 0, negative 3.68. And I can plug in F12, and so 318.59, 245.24. And I'm going to move everything to the other side of the equation, I guess. So let me rewrite this. So RAX, RAY is equal to negative of this plus 0, positive 981, plus 0, negative 368, and I got negative 318.59, positive 367.76. So all of this stuff, I mean, it's pretty easy to imagine extending this approach to linkages inside machines or engines or things. And this is the kind of analysis that you would do to figure out how strong the parts have to be, what materials you have to make the parts out of, you know, how thick they have to be, that kind of thing. Okay, any questions? All right, that's all for today. So I'll just give you some more problems like this to work on. And we'll do this for a couple more days and then we'll move on.